Okay, in this module, we're going to look at something called recurrences. So recurrences can be used to study the time complexity of some types of algorithms that we haven't looked at again. So for context, we're going to look at Heapify yet again. Just for review, Heapify is the process of fixing the order property when you're going down the binary heap. So it's used as part of the remove or extract process. So in case you don't remember, when you're removing nodes from the binary heap, you fix the shape property first by moving the bottom rightmost leaf up in place of the root. And then you use this process referred to as Heapify to move down the tree. Okay, one of the things that you may not have thought about is that heap is binary tree, and that it can be expressed recursively, that if you think about either the left tree coming off of the root or the right tree coming off of the root, each of those would be a valid heap in and of itself. Okay, so for example, the left side of the tree would be a valid heap all on its own. The right half of the tree would be a valid heap all on its own. That's kind of useful because you can think of heaps as being potentially defined recursively, and almost anything that can be expressed recursively like this can also be processed recursively. Okay, so let's go ahead and express the Heapify algorithm as a recursive algorithm. So we'll define the Heapify algorithm as starting at a particular node. The first thing we need to do is find the child of that node with the smallest value, and then we'll compare the original node V's value to the value of its smallest child. If V has a greater value in our min heap, we'll need to swap it down with the minimum child's value. So we'll do a swap. And then we can start the process over recursively at the subtree. So we'll do a Heapify starting at that smaller child. Okay, so again, just a recursive definition. Also keep in mind that the subtree is smaller than the original tree. So the problem gets smaller as we progress down the tree. So that's kind of an important property with recursion. You almost always want to make sure that you've got a base case, and you want to make sure that your recursive case is working on a smaller problem, a problem that somehow is getting closer to the termination criteria for the algorithm. Okay, in terms of the time complexity stuff that we've looked at, we have a bit of a challenge here because we haven't done anything that we could use to express the complexity of recursive functions like this. So the way we're going to do this is by using recurrence equations. So basically these are equations that look somewhat recursive. They're an equation where the left-hand side is usually used as a factor in the right-hand side. So let's set up a framework we can use to talk about these recurrence equations. So we'll construct some terms. So first off, our goal is to come up with a function that represents time. So that in particular, we want to express the time taken on a problem of size n, or the number of fundamental operations, if you prefer. So since we're really looking at time, we'll use the letter t. So we'll use the function t of n to generically refer to as the time taken to solve a problem of size n. So every time we look at a different algorithm, we'll use the same terminology. We'll look at the t of n for that particular algorithm. Okay, so we need a way also to keep track of the amount of work that's not involved in recursion for a problem of size n. So again, we'll come up with a generic way of expressing that, and we'll express it as a function of n. It may be dependent on the actual size of the instance. So we'll use f of n, just some generic function of n. Okay. We also need a way to think about how much smaller the problem gets as a process of recursion. So in our Heapify, remember that the tree gets one level less tall each step we take. The overall height of the tree decreases by 1. Again, to keep things generic, we will use a function. We'll say that this is a function of the size of the problem n, and we'll just refer to it as g of n. Okay, so we've got these 3 different terms that we're going to be using. T of n represents the time taken on a problem of size n. f of n represents the amount of work we have to do at an instance of size n outside of the recursive process. And finally, g of n represents how much smaller the problem of size n gets for the recursion. Okay, so putting it all together, we can express the amount of time it takes to solve a problem of size n in terms of the amount of non-recursive time at a problem of size n, the f of n, plus the amount of time it takes to recursively solve the subproblem. So we have to figure out the size of the subproblem, that's our g of n, and then we will recursively solve that subproblem, the t of g of n. Okay, so this entire equation represents the concept of a recurrence equation. So again, kind of notice that it appears to be recursive in a sense. The right-hand side of the equation uses the equation itself. Okay, so our goal here now is to use our Heapify algorithm as an example and try and develop a recurrence equation for Heapify. So, starting with the form of our recurrence equation, t of n equals t of g of n plus f of n. Let's go ahead and try and figure out the right-hand side of this equation, the f of n and g of n. So looking at our pseudocode for our algorithm, there's this process of finding the child of v with the smallest value, and then there's a simple if statement. So there are only two children. There are always exactly two children. It's a binary tree. No nodes have more than two children. So we could argue that the first part here is a constant time operation. It's going to have to do a couple of different comparisons to find the smallest child. A comparison to find the smallest child, and then it's going to have to do a second comparison to compare to v, so a total of two comparisons. I'm going to argue that that's some sort of constant time work, and I'm just going to pick some arbitrary constant to represent that k. So that gives us the amount of time that's spent working at a particular instance. It doesn't really matter what n is. We're always going to be trying to find the smallest child and see if the current node's value is greater than that smaller child's value. So the f of n is a constant k. Okay, so we found part of our recurrence. Next, we have to try and figure out the g of n part, how much smaller the problem gets. Okay, so that's going to take just a little bit more effort. So our goal here is to find an upper bound, a big O. So we may be just a tiny bit pessimistic. So by that I mean we've always got two different subtrees. We want to make sure that we pick the larger of the two subtrees. Okay. Of course, we also need to express our function in terms of n. Okay, let's take a look at our tree in terms of its two subtrees. So we've got our tree here. We can think of this as a complete or a full binary tree. So we've got our root node, and then it has two subtrees, a left and a right subtree. Okay, we've got some theorems that we've established in a previous module. We know the total number of nodes is 2 to the height plus 1 minus 1. We also had a lemma that went along with that kept track of the total number of leaves. So the total number of leaves is 2 to the power of h. So in this complete and full binary tree, on our bottommost layer down here, we have a total of 2 to the h leaves, and that's if our entire tree height is h. Okay. Okay, so consider that we have n nodes and two subtrees, but imagine that it's not full on that bottom layer. Imagine that only one of the two sides is completely full. So let's figure out how many total nodes we have in this particular tree. And first of all, just note some properties. The overall height of this tree we could consider to be h. And the height of the left subtree we would consider to be h minus 1. It's one step lower than the root. And the right subtree would then be h minus 2. In our case, we're going to be slightly pessimistic and think about the maximum amount of work that we would have to do, which would be all about the taller of the two subtrees, which would be the left subtree. Okay. Oh, and by the way, keep in mind that we're looking at this example partly because this fulfills the shape property requirements of our heap. Remember that the heap fills up from left to right and bottom to top. I'm sorry, top to bottom. Okay, so our heap isn't always full. So let's imagine that we have a full heap, and then we'll get rid of those leaves that we lose when it's not completely full. So if you remember, our equation for a full heap of height h would be 2 to the power of h plus 1 minus 1. Okay? And then we want to get rid of the leaves on the left-hand side. So that would be half of our available leaves. And remember, our lemma gave us the equation for total number of leaves, which was 2 to the h. So half of our leaves would be 2 to the h over 2. Okay, so the total number of nodes in this tree can be expressed with an equation, and we can simplify that equation to be 2 to the power of h plus 1 minus 2 to the power of h minus 1. Okay, so it's a little bit messy. At some point, we want to kind of simplify things so we can combine terms together. So before long, we will look at this, and we will try and re-express things in terms of 2 to the h minus 1. Okay, so let's focus on that larger subtree. So we found out the total number of nodes in the entire tree. Let's think about the larger subtree, that left subtree, and figure out how many nodes are in that subtree. So for the time being, we're considering that subtree to be completely full. It is a perfect triangle. And we can use our theorem and fill in the blank. So our theorem is that the number of nodes in a complete perfect triangle size tree is 2 to the power of something, the height, plus 1 minus 1. And in terms of our original problem, the height of the overall entire tree is h. The height of this subtree that we're interested in is h minus 1. So let's go ahead and fill in h minus 1 into our theorem. And we will get 2 to the power of h minus 1 plus 1 minus 1. And of course, we can simplify that down just a little bit to 2 to the power of h minus 1. Okay. Back to our overall goal. We are trying to find this function, g of n, that describes how our problem changes recursively when we go from a problem of size n to a smaller problem. Here, we can do that by expressing the subtree size over the full tree size times n. So we can try and find the ratio of the sizes of the two trees. So we've got our equations that we've just developed. The overall subtree as 2 to the power of h minus 1, and the overall larger tree with the right-hand subtree not having leaves at the same level as the left-hand subtree is 2 to the power of h plus 1 minus 2 to the power of h minus 1. Oh gosh, that's a bit of a mess. So as I mentioned earlier, we're going to try and combine together terms, and we'll use the h minus 1 term as the kind of our way of attempting to combine things together. So let's try and take this messy equation, and we'll refactor a little bit and express everything, all of the 2 to the power of something in terms of 2 to the power of h minus 1. Okay, so thinking about the numerator here, we can express 2 to the h as being 2 times 2 to the h minus 1. Okay. And we can do a similar sort of trick with the denominator. 2 to the h plus 1 we can express as 2 times 2 times 2 to the h minus 1. So we're just dividing 2 off of them, which subtracts 1 from the exponent. And the denominator, we do it twice. We divide off 2 twice. So we can express it like this. Everything now has a kind of a common exponent. And now we can start combining things together and simplifying a bit. Simplifying the denominator first, we can multiply out our 2 times 2 and have that 4 times 2 to the h minus 1 minus 1 minus 2 to the h minus 1. Oh gosh, so we've got this and this. So we'll subtract off that second one and simplify just a little bit further. And we'll get a numerator of 2 times 2 to the h minus 1, and the denominator of 3 times 2 to the h minus 1, minus 1. Okay, so thinking asymptotically, we can think about the limit of this as our height approaches infinity. And essentially, it will simplify down to 2/3. Our 2 to the h minus 1 terms will essentially cancel each other out. The subtraction of the constants will be insignificant. Okay, back to our overall Heapify thing. We are trying to figure out this recurrence equation. We've already figured out our f of n is just going to be a constant for the constant time work we do at each level. And we have now figured out that our g of n is 2/3. Each time we move down the tree, we've got 2/3 the number of nodes that we might have left. And that's our maximum. It'll always be less than that. If we had gone down the shorter subtree, it'd certainly be less than that. If the subtree isn't absolutely full, it could be less than this. Okay, so at this point, we have finally built a recurrence relation. So our entire recurrence equation is, in order to solve a problem of size n, we have some constant work, k, at that problem size, and we have to recursively solve a problem of 2/3 of n in size. Okay, we've got this equation. Now what? Okay, so one of the things we could do with this equation is we could try and apply it. We could try and actually do some computation with it. So for example, we could try and figure out how much work it takes to solve a problem of size 100. We could just plug in numbers and continually refine this using this recurrence equation. So in order to solve a problem of size 100, well, we have to solve a problem that's 2/3 that size and do some constant amount of work. So we'd have to solve a problem of size 66 and do our constant amount of work. But we can substitute this, our t of 66, into our recurrence equation. And in order to solve a problem of size 66, we would have to solve a problem of size 44 and do some constant work. And also we have our constant work for the problem of size 100. Gosh, so how much effort does it take to solve a problem of size 44? Well, we can plug it into our recurrence equation. We have to solve a problem that's 2/3 this size and do k units of work. So 2/3 of a problem of size 44 is a problem of size 29, and we have our constant work that we have to do. You get the idea. We could continue applying this over and over and over again. And eventually we end up with some sort of a base case, a problem of size 1 or a problem of size 0, and a whole bunch of k. So I'm going to assume that a problem of size 1 takes no significant work. I'm sorry, a problem of size 0 takes no significant work. And at this point, we have a total of 10k. Okay. So now kind of a brief aside. So if we think about computing with t of 100, and we ended up getting 10k out of that, what if we'd had a bigger problem? What if we wanted to find out the amount of time it takes to solve a problem of size 150? Take a minute and think about this. Well, to solve a problem of size 150, we could fill this into our recurrence equation, and we'd have to solve a problem of size 2/3 of 150 plus our k units of time. Okay. Of course, 2/3 of 150 is 100, and we've already solved that. So we could take the work that we've already done, the fact that t of 100 is 10k, and add another k onto it and get 11k. Okay, so we have some way of kind of using this to generate or figure out the total amount of work being done. So we still have to, at some point, tie this back to big O or big theta. And eventually we'll show that these t functions can be used to demonstrate something about big theta. And in this case, we'll eventually get to showing that this algorithm is log n. Okay, so we can use this to generate some computational complexities. So just to take this one step further, we'll expand this example out a little bit by looking at a spreadsheet that does the computation for us, and then we'll also graph out the complexities, and we'll see kind of a familiar pattern. Okay, so here's an example spreadsheet. The first column shows values of n, so this would be our problem size. The second column shows 2/3 times n, and the floor of that, so rounding down. So basically, this is kind of computing which row we should go to get our time complexity. And the third column shows the total amount of effort we have to expend. So it's the t of the smaller problem plus the constant k. Okay, and then the fourth column d has the constant k. Okay, so just as an example, in order to solve a problem of size 12, we're going to solve a problem that's 2/3 of that size, so 8. So it will go up here and take the total amount of work from a problem of size 8, and it will add a constant amount k onto that. So 20 plus our constant k is 5, gives us the 25 to solve a problem of size 12. Okay, over here to the right is a graph that's showing the different time complexities. So it's kind of a step function because of the integer division. And it's kind of showing that as n increases horizontally, the amount of work goes up, and you can see kind of the slow, gentle slope here. Okay, so using that spreadsheet approach to kind of generate the total amount of work that's done is accurate. We can compute exact values, but it's really, really awkward. Okay, so our goal is to come up with a closed form equation to get rid of these recurrences and have an easier way to compute the overall result.